Hello and welcome to the session. I am Akshay Kumar and I'll be discussing with you about procedural calls in 8086 assembly language programming. I'm working as Associate Professor in School of Computer and Information Sciences of IGNOU, and this program is for our MCA, BCA and PGDC students who can refer to their course material about Block 4, Unit 4 of MCS 12. Now, what is a procedure call and why do we require procedure calls? Well, the logic boils down to something called modular programming. Now, modular programming is primarily divide and conquer kind of technique where a given problem, a big problem, can be broken down into smaller problems, right? So, those smaller manageable problems which are distinct from each other. And actually modular programming led to object-oriented programming where the concept was brought in, where object used to do everything for the given module. But modular programming is just a prior concept to the object-oriented programming. So what does it do? Basically, it breaks large program into smaller modules. Alright, so small procedures or functions which can be utilized. Then it allows linking of object programs from many different source language. Now this is a very important advantage. Many a times you will be hearing from us that operating system is written in one high level programming language like C or C++ and assembly language programming. Now we are writing programs into two different languages, right? But their object programs can be combined with the help of modular programming by using parameter parsing and so on and so forth, so that we are able to do the linking of those programs and we are able to execute a monolithic program out of it. It's not monolithic, but it consists of several parts, right? Now, easy creation, maintenance and reuse of module. Now, this is another important advantage of modular programming, and so is the case with the object-oriented programming. Because the smaller are the modules, the easily they can be created, easily they can be tested, easily they can be maintained if there are some changes needed, the complexity is manageable, right? And in addition, they can be reused for different programs. For example, if you go through stacks and other kinds of data structure, right? You will go through them in semester 2. There, when you implement those data structure, right, and as a template, then you can reuse those templates in any other program. And they are very small programs. They are very small modules which basically perform stack-oriented operation. Why I named stack? Because we will be using stack in this particular session and we will be discussing about it in more details. Then manageable debugging and testing can be done. So this is what actually I was referring to. The smaller is the module, the easier is the debugging, easier is the testing. However, there are going to be additional need for integration testing, which we will be studying in the software engineering parameter. Okay, and maintenance of local modules only. So you are required, suppose you have created some local modules, then you just need to maintain those local modules. If you are using the modules from the library, then library is maintained by somebody else. And this is, if you see, this is what is happening these days, right? It may not be the modular programming, it may be moving to the object-oriented programming domain, which is slightly advanced than the modular programming in the sense of that is the controls and the safety kind of a situation, but and the security, who can modify what data and like that, those kinds of situation. But basically they have started from the modular programming, and this is what you can actually get the basics of it. Now what happens? So basically modular programming is that we create a lot of procedures, right? So if I have created 5-6 different procedures, obviously I'll be calling those procedures. In C programming, most of you must have done C programming by now. So you write functions and main function calls function A, function B, function C. So let's say a main program or a function A calls function B. So what happens when a function called A calls function B? Remember, even main in C is a function, right? So how these procedure and function, basically there are slight differences between the two. You can study in the material, but basically they are as far as concept is concerned, as far as implementation kind of thing is concerned, the function and procedure are same. Function just has one return value, right? Okay. So now when A calls B, what happens? The return address. So A is calling B. So a particular statement of A will be calling the function B, right? So that statement, actually when you are executing that call statement, where is your program counter? Already onto the next instruction, right? So that next instruction actually is the return address, because call should take the program to the another function, that is B. So now B code should be executed, and when B returns, it should come back to the next instruction after the call, and that address is already in the program counter. So it must save the return address of the next instruction, right, which happens to be in the program counter for returning back to calling program. So this responsibility is with the call instruction. So when you are executing the call instruction, the responsibility of where the return address is to be stored, right? And technically it is going to be stored in a stack. And what is a stack? It's stack of books, right? You have stack of books. How does it happen in the house? Many a times when we are studying, we create stack of the book over other, and so on and so forth. Now, what is the property of that particular stack? We can pick up the book only from the top. If we try to pick up a book from the middle, probably the stack will crumble. So we can pick up the book onto the top. So basically, last in, whatever is the last book which has been put onto the stack will be first out, LIFO, last in, first out. So that is the property of the stack, right? So this is how stack is basically identified, and this is how the data structure stack is basically explained. Okay, so now, with whose responsibility it is? What going back to the call instruction, and the call instruction will be putting the return address, right, onto the stack. So if A calls B and B calls C, then B's return address will be put onto the stack, onto the top, and the returning sequence will be C will be returning to B, so top of the stack will be containing the return address of B only, right? And then B will be returning to A. So that way the forward movement and the return movement or return basically takes place as far as procedure calls are concerned. Then we store registers whose content is changed by the called procedure, because this is basically what we call is the side effect of procedure call. If a procedure A calls procedure B and procedure B changes some of the registers which were actually being operated by procedure A, then the value of those registers will get changed, and that should not happen. Because when the procedure B returns to procedure A, all the initial values of those registers should be maintained, right? Because procedure A has its own set of values in those registers, and those, if changed, may cause erroneous execution of the program. Okay, so we'll see this particular thing when we take up an example. So this is what is a very important consideration over here, that all those registers which are processed by B, right, procedure B, must be saved. Those content which will be changed by B, okay, B knows what I am doing, okay. So B knows, or B programmer, whoever has written B, he or she knows what registers it may be changing and so on and so forth. This is an assembly instruction right now we are referring to. So it is going to actually take care of that particular thing. Otherwise, the compiler has to take care of this particular step. Then passing of parameters to the procedure. So you must have noticed in function calls, some parameters are passed, right? Maybe call by value or whatever. So those parameters, how they will be passed between the procedures. So procedure A is responsible for putting those parameters, and there has to be an already agreed upon mechanism that this is the way we will be passing the parameters. So that agreeable procedure as well as procedure A will be responsible for passing where exactly it will be passed. If you remember, when we discussed about reduced instruction set computer, there was a window, like there was an overlapped window within the processor. So the parameter passing in those cases were directly through the registers, right? So that is one possibility which exists, but here we will be discussing in a slightly different way. Once again, we will be discussing about the stack, because stack is going to be one of the major data structure whenever we are dealing with the procedure call. So let's move to the next statement. Now, whenever we are doing the procedure calling, we need stack segment technically. And stack, what is shown over here, is nothing but an array, right? No, it's not an array. It is primarily a type of array which is, let's say, which is closed from the bottom. Okay, so in assembly language, the stack grows like it grows from top to bottom. This is slightly different from normal stacks which we use. Normally, in normal stack, we start from the bottom of the stack. It keeps on growing. But in assembly language programming of 8086, right, the stack grows from top to bottom. And as soon as, now this particular pointer which you are seeing is the bottom of the stack, which basically is pointed to by the stack point, that is SS, stack segment register. So stack segment register, technically it is stack segment register is just a segment register. So it points to the base, right? So it points to the base, and that particular base is over here. Okay, now what you see over here, okay, now this is initial position. This may be the initial position of the stack, and as we put some values like what you can see over here, CS high and CS low, that is put into the stack, then IP high and IP low has been put into the stack, and that is where the pointer or the pointer to the stack is basically pointing to. So code segment and the instruction pointer, both have been saved in this particular case. We'll talk about why these two has been saved and in what case these should be saved. But for the time being, you look into the top of stack pointer. So this basically is top of the stack pointer, and it grows in this direction and shrinks in upward direction. Grows in the lower direction and shrinks in the upward direction. This is, once again, I am repeating, right? So this is how the stack works. Okay. Now stack, that means stack will be full when this pointer reaches this pointer, right? So that is where the stack will become full. So then that means one more word will be stored in the stack. Now, another important thing which you need to learn, what this memory shows is a byte, right? So this is one byte, this is another byte. However, when we are dealing with stacks, it is dealing with the data words only, right? So how many bytes is data word in this 8086? Because byte is 8 bits and one memory word and the data word is 16 bits, right? So 2 memory words. So at a time when we put the value, for example, when we are putting CS, so we are putting CS high as well as CS low in one go within the stack. Okay. Similarly, IP high and IP low is one entity within the stack. So a stack is basically consisting of data words only. Although we are showing it as a, obviously we have to show it as a data byte because memory is organized as byte. Otherwise, these two basically forms the CS, and they are put in one go. Similarly, IP in that particular sense, right? So this is how we deal with the stack. Now, when we are dealing with the stack, we need to declare the stack segment in the assembly language programming because we are dealing with the segments. Okay. Now, when we are dealing with the segments, so just like data segment, there is a stack segment. Okay, and within the stack segment, we declare how big the stack is. All right. So this is 100 word stack, right? So basically 200 byte, right? So this is what it indicates. And top of stack has to be pointed to by some pointer. So that is also a word pointer, and top of stack TOS, right? Top of stack is the label which will be this particular pointer when we will be using the stack. This is how it is going to be represented over here. Okay, so this basically defines how data words are going to be organized in stack. Stack segment register stores the bottommost address. Now, you may be wondering, it is 20-bit address. So, top 16 bits are stored in the stack segment, right? So, bottom, the 5th bit is going to be 0, right? So, this is going to be the 0th bit, and that is how the stack segment will be allotted in this particular sense. Okay. Then code segment, how the stack will be initialized, right? So, the initialization of stack, just like what you did for the data segment, initialization of stack is also to be done, okay, and it once again depends from compiler to compiler. It may change, this particular kind of a setting may change, right? So, you really need to look into different compilers, what you, in fact not compilers but the assemblers, whatever you are using for assembly language programming. Okay. So, what you are doing here is basically you are moving the address of stack segment, right, into the SS, and you are moving into AX register, and that you are moving into the, that is the address of basically the top 16 bits, basically where the, it will be loaded, will be stored in the SS register, stack segment register. And the SP, stack pointer register, right. So, the pair is SS, SP, okay, they jointly form the physical address. So, SP is the stack pointer, which basically is an offset, right, from the SS, okay. So, when we add SS into 16 kind of a situation, you remember how we calculate the physical address, SS into 16 plus SP, that is how we are going to calculate the physical address. So, SP is going to be loaded by the top of the stack, which technically is going to be the topmost location, right, above, that is the topmost location in the first code, that is beyond when we are initializing. And this is just the representation for the stack segment, which we have not done yet. Now, what operations we provide so onto the stack? And another thing which we will be discussing in this slide is near and far calls, right? Okay. Now, what happens when we push onto the stack, right? Now, we can push, we are pushing word by word, right? Word by word means we can push CS, we can push IP, or we can push CS as well as IP when we are making a procedure call, right. So, one push is basically for one value. So, if I say push CS or push IP, so this is what is going to happen. So, these two are separate instruction, push CS as well as push IP. Both will be separate instruction, and what is going to happen during that particular instruction is given over here. The stack pointer, suppose the stack pointer was here, okay, that is decremented by 2, all right. So, suppose you have said push CS register, right. So, when you say push CS register, then stack pointer register will be decremented by 2, and SP1 plus 1 SP location are assigned the source. These are stack pointer will be decremented by 2, and this SP plus 1 and SP, whatever is pointed to by SP and the next location, right. Why? Because they are 8 bits, right. So, SP is pointing to, it is decremented by 2, SP is now pointing to stack pointer is pointing top of stack or stack pointer, right. So, top of stack is pointed to by SP register, be very clear, top of stack by SP register. So, SP is pointing to this particular location, it gets the lower byte, okay, of the CS, and SP plus 1 happens to be this location, it gets the upper byte of the CS register. That means this is how the CS has been pushed into the basic that is the stack. Similarly, IP will be pushed likewise, okay. Okay. Now, the other operation which you will be doing will be pop destination. So, you will be bringing that particular information into some location. So, destination is assigned, stored at the top of the stack. Suppose I say pop, right, then and my position is IP high and IP low like this, or let us say IP high and IP low in this particular case, right. So, my SP points to this. So, first whatever, suppose I say pop AX. So, AH will get IP high, AL will get IP low, right, and those values will be assigned, and then stack pointer will be incremented by 2. So, it will reach to this particular position, all right. So, this is how stack pointers moves, all right. It goes up when the stack is full, when this pointer reaches the stack segment pointer, Alright, so this is how we will be coming to know that, okay, that offset 0, right? So when we reach the offset 0 with the stack pointer, that is the time when the stack is full. Otherwise, stack grows in this direction, stack shrinks in this direction. Push puts you down, takes you down, and pop takes you up. Right? So this is a low address and this happens to be the high address. That is why this SP is going down by 2, -2. So we are moving into this particular direction. Now what is near and far call related to this particular thing? Well, these two procedure calls are very, very important to understand. First of them is the near call. Now when we are making a near call, the code segment, right? The code segment is the procedure is within the same code segment of 64K. Okay, one segment can be of maximum 64K. So if the procedure is within the same code segment as of your main code, so then this is called a near call. That means if suppose I am having lots of instructions over here and they are into the same code segment, so then it is called a near call. Why? Since the segment register value is not changing, CS is not changing in this particular case. So what is changing? Only IP, right? So the return address which will be stored will be the IP high as well as IP low. So suppose the initial top of stack, that is SP, is pointing to this particular location, it will be decremented by 2, then IP low and IP high will be stored here, right? So and then now the new stack pointer is this particular value. So this is how the procedure call is going to take place. And in case it is a return statement, these two values will be picked up, right? And the whatever is the return value or basically this is the next instruction which is going to be executed by the microprocessor, right, in the next. So this is what is going to be loaded into the program counter register, so that this becomes the next instruction to be executed. So this is how it works. So this is a near procedure call. In the near procedure call, my instructions are within the segment, right, within the same code segment. However, there is a possibility when my code segment makes a call to a procedure which is not in the same code segment but a different code segment. If that happens, in that particular, this happens when you are using, if you are using small, the small coding like .small or something in Microsoft kind of assembler, then you are dealing with the near procedure call. Whereas far procedure call, when you are using the large or medium kind of process where there can be possibility of more segments, more code segments in that particular situation. Remember, at a moment of time when a program is executing, only one code segment will be operating because there is only one code segment register. Right? But then we can shift from one code segment to another code segment, right? So that is possible. So this is what we will be doing if we are making a far procedure call. In case of a far procedure call, we are moving to another code segment. If we are doing so, then we will be required to store the code segment as well as IP, both. So CS IP pair, both will be put onto the stack. So it is the assembler whose job is to remember or to find out whether it is a far or it is a near procedure call, and accordingly stack will be adjusted by the assembler. Alright. So this is how it works as far as procedure calls are concerned. But let's look into an example and then we will be very clear about this kind of a situation. Now what we are doing is parameter passing through stack. There can be possibility of parameter passing through registers. We are not going to do that. You can learn it if you know this particular parameter passing through stack. You can learn any other kind of, there is an example from the memory also as far as your block is concerned. But if we do this, you will be able to understand all those two very, very easily. So now what we are trying to do, first of all, we are doing the modular programming. If we are doing modular programming, we got to create a procedure. Now, if in this particular case, we might be creating a near procedure, right? Near or far procedure, it is not making much of a difference from your perspective, but you need to know about them, because if you are operating into the near or far domain, how the pointers within the stacks are to be adjusted to refer to different data items. So, since we are doing the parameter passing through stack. Okay, so now the objective is we want to convert BCD, right? There is a number which is BCD, let's say 25H hexadecimal, and you know binary coded decimal. So, this is basically a decimal, although it is a hexadecimally stored, but this is 2 and a 5, and we need to convert it into binary. So, binary, if we convert it, obviously the equivalent decimal we are trying to say, then obviously it is going to be 19 in hexadecimal. So, we want to convert this BCD number into equivalent binary, which is going to be 19 as far as hexadecimal is concerned. Now, how to do that? Now, that logic is slightly different. Let's utilize how we can utilize the procedure call and parameter passing in this. Now, what parameter is to be passed? The value of BCD. What value will be returned? The binary value. And what we want, these parameters are passed through stack. So, we will be putting the value into the stack, and the return value is also expected to be back onto the stack itself, and how it can be done. Okay. So, obviously the stack segment is to be declared, because we want to use the stack segment. So, we have declared the stack segment, and the top of the stack we have put top stack, because this is what we are going to be using, but this is how it works, and then stack of 100 words you have declared, and then all the segments are assumed as the usual case be. Now, the calling program. Now, the calling program moves like this. Okay, so first the data segment is to be initialized, so you can do that using already known process, where the some of the compiler use @ before data, and that is just making it as a immediate operand and so on and so forth. So that you can check with different kind of a assembler or different kind of a module, the emulator, that you need to change accordingly. But the important thing is the logic, that we are loading the segment address into DS register. Okay, so that is what is important. So, segment register is going to be the upper four hexadecimal of the 20-bit location, right? So, this is what you need to understand. Similarly, the stack segment is going to be uploaded, right? Using the stack segment, this particular thing we have already done, offset top of stack. So, the stack pointer will be moved into the stack pointer. Okay. So, we have initialized the stack, which is going to be top, right? Top is going to be at the topmost element. Okay. Now, what we are going to do? So, since we want to pass the parameters with the help of stack, where exactly is the parameter? The parameter was in the BCD location, right? So, what we are doing? We are moving the content of BCD location into AL register. Since it is data byte only, so AL will do, right? Okay, so we have moved it to it. Now, why we have pushed AX? As I told you, once again remember, when we are operating with the stack, right, we are dealing with words, right, and AX is basically 16-bit, it is one word, right. AL is the lower half, 8 bits, right. So, AX will be pushed into the stack, because stack deals with words, no possibility of dealing with bytes. So, if you want to put a byte, you need to convert it, you need to push the word into related byte. So, AL contains the data, AH contains nothing but need to be pushed. Now is the main statement over here. So, what we are saying, we are calling a procedure call BCD binary, but where is it defined? So, we have not yet defined it, do not worry, we will define it, alright. And then comes the pop statement. Once the procedure call is over, the next statement is the take the value from the stack to AX. So, what you are doing, remember this particular thing, you are pushing it to AX register. So, you are passing your parameter through stack and then extracting the return value from the, so this basically calls that particular function, and the return will bring you to the pop statement, and at the pop statement the value of AX will be coming from the stack. So AX will be loaded by the value of the stack, which should be the converted BCD to binary value, which is the role played by this BCD binary procedure. So we'll see how this BCD binary procedure is working and all that particular thing. And then finally we move this into binary AL. So we can move it into the binary location, that is binary this location. So this will be put into the whatever is the converted value, happens to be 19H. So it is going to be put in this particular location. And therefore thereafter no operation or whatever, basically the program will continue, and this basically just shows okay, the remaining program comes at this point of time. So this is my calling program. Calling program statement is over here. Within the calling program, these are the simply initialization of data segment, which you already know how to do it. Then we will be initializing the stack segment, which we discussed before. And once we have done the stack segment initialization, how data segment initialization and stack segment initialization is different. The only difference is that in the stack segment initialization, stack pointer is also initialized, right, to the top of the stack. Alright, so this is how the stack pointer and stack segment works. Okay, so we go to then the procedure, how we are going to write that procedure. But important thing is just over here. So before we executed the push AX statement, so we have assumed that there were already some stack movement, and we are, although it was 100H, it could have been there, we are just dealing with 0090H, right? So this is and as I said, 200 bytes, no, 100 is actually 256 bytes, right? So that is what, so we are just moving on to this hexadecimal location, and we are assuming that this is already there. So as soon as we push AX by the calling program, stack is decremented by 2, alright, and AH and AL will be stored over here. Where exactly our parameter? Maybe in AL, but stack push is concerned, AH as well as AL is concerned. What is the next statement in the previous case? The next statement happens to be call BCD binary. Now call BCD binary, in our case, since we are assuming it to be near procedure call. So what you see, the next thing which is going to be here is IP high and IP low. Alright, so this will be the call instruction which will be putting IP high and IP low, and why? It should be a near procedure call. That's what we are assuming. So let's look into the procedure, whether it is near procedure call or not. If not, then we are in error. Okay, so this is how it works. BCD binary proc near. If we put proc far, then the calling procedure will put CS also in addition, right? But since we have claimed it to be near procedure call, so we know exactly how the pointers are going to be addressed. Now what we are doing? So when you are writing a procedure, so this is the procedure. How we are declaring a procedure? First statement is the declaration of the procedure, and the name of the procedure is BCD binary. It is a procedure, so we are indicating the proc, right? And near, so it is a near procedure. That means within the same code segment, this procedure is going to be assembled, right? Okay, now this particular procedure, the very first register which we are pushing, right? It is a flag register. Why? Because you remember what we said, that the flag stores the last arithmetic operation instruction. So it should not be destroyed in the calling program. Alright, so that whatever, suppose it is doing some operation onto that particular flag register, it should not be destroyed. Alright, so this push flag, right, is the first thing. So flag register should be pushed into the stack, followed by AX. AX register should be pushed into whatever is the value of AX will be restored. It may be, in this particular case, although we are using AX to store binary value and then pushing it, but then our objective is that we restore that particular AX value, whatever it was, right? Because when we pop the value, need not we pop it in AX register, right? So AX should be restored because this particular program is going to destroy AX. So push that value. Push BX. because Bx will be utilized. So how we are going to use, we will be seeing. And then BP because BP will be used, we will be using the stack pointer and will be using the BP register. So BP register. So this particular procedure is assumed to be using flag register, is mostly pushed. AX, BX and CX, which will be utilized in the process. BP is already being utilized, you can see. BP is loaded to by the SP value. So this BP is going to be obviously utilized. So the value or old value of BP will be destroyed. Therefore, all these registers will be pushed before we perform any of the operation. Okay, within the process. So the first few statements will be pushing all those registers which will be dealt with by this particular procedure, or which will be destroyed, or which will be controlled, which will be changed by this particular procedure. Okay, so 1, 2, 3, 4, 5, right? The 5 registers we have pushed. So let's see that particular stuff. IP high, IP low because of call. Flag high and flag low because we pushed flag register. AH and AL because we pushed AX register. BH and BL because we pushed BX register, CH, and finally BP high and BP low because this is what we pushed at the last, right? So now what you see, after pushing BP, our stack pointer is 0082H. So this is pointing to this particular location. Now, no, not line, just forget this particular pointer anymore now. So our pointer is pointing here. And where is our data? Somewhere here, which we push. The parameter is somewhere here, whatever parameter is to be used. Binary, that is the BCT value is in AL register, which is far suppressed into the stack, right? So this is what we want to get back to and get that particular value. And stack segment, this is segment register, remember? So if you see, then this will be 000H technically speaking, okay? So this is how this whole stuff is going to be, okay? So now what is this particular statement? What we are saying, move AX BP plus 12. Now first we moved stack pointer register into BP and then added 12 to BP, and then we have moved it into AX register. Why did we do that? Okay, so the explanation is there. BP plus 12 location, 5 push statement plus 1 call, which is intra segment, within the segment, that is the near procedure call. So just IP is stored. So total of 6 words are pushed after. Had it been inter segment, that is far procedure, then it would have been 7 words because CS would have been stored in addition. Then we would have got it as 14. Alright, AX has been pushed and it is a word in a stack. So BCD value which is stored is 12 location under stack, hence BP plus 12. So this particular diagram basically explains. So you can count 2, 4, 6, 8, 10, 12, and that is after 12 AL and AH. We have reached to the AH and AL. So that is what is the significance of BP plus 12. Alright, so BP plus 12 primarily moves us, okay, BP plus 12 primarily moves us or moves this particular value. Okay, so whatever we will be extracting from stack BP plus 12, right, whatever is pointing to by BP plus 12. So we are just using the register value BP, okay, and the adding 12 to it, and that becomes the reference, okay. So the value stored at BB plus L will be stored, that means what was the value? AL and AH. So that will be brought into the AX register, right. So this is how now my AX register contains the BCD value. In fact, in AL register only it will be the BCD value. Now that BCD value has to be converted. So what AL contained? 25, right? So we move it into BL, and now 25 is to be converted into equivalent binary, right? This is a BCD value, right? So we divide it into 2 places. So AL and BL, both now contain 25. Both will contain, because we have moved AL into BL. Then BL, now we are using 0F, right? So what will be extracted? The lower 4 bits, right? They will be extracted in BL register, right? So BL now will be converted to 0 and 5. So upper 4 bits will be masked out because of 0FH, and in AL the lower byte will be masked out, so it will be 20. And then we move 4 to the pointer, that is CL register, because we are making 4 cycles of movement. So by moving it 4 times, what we will be getting, this 2 will be moved to here and 0 will be moved here. So now we got 2. So we technically in BL now we have got the lower byte, the lower nibble, that is 5, lower digit, and in AL we have got the upper digit, that is 2. So now what next we do? We multiply BH, right? We multiply, move into BH, we move 0A and multiply BH and BL. So this is how we will be getting this particular, in fact it should be BH over in this particular case. So when we multiply it by, we get 14H, right? And then when we add, right? So AL will be multiplied, remember that. AL, right? So when we are multiplying, we are moving 10 into BH register, and when we say multiply BH, what will be multiplied? AL will be multiplied by whatever is the content of BH, which happens to be 10, right? So this 2 into 2, this we will get, and right, so this is the 10 value, and we will be getting 14H, which is the binary value, and in this particular binary value you will be adding BL, which happens to contain 5, so you got the 19H, which is the equivalent binary, or in a sense hexadecimal value in this particular case. Now once you have obtained this particular value by processing, now this is your program logic, and this kind of program logic we have covered in many different programs, and we have discussed them through this particular channel, our live session also. So you can once again go through this particular logic of the program, and if you have any query even in the logic, you can mail to me, or you can join the MCS 12 group which is there on the Facebook, and give your query over there. But the important thing is, now this value, whatever we have obtained, right, in AL register, right, and that AL register now contains the value, AH contains 0, because that is, or AH contains whatever, it does not matter, right. So now our AX contains the converted BCD value, right, which is now in the binary. So it is to be pushed back into this place, right? And where exactly it need to be pushed back? Once again to the same place where the parameter was passed. That is why BX plus 12 gets the value of, so that means this AL now will be changed to the binary. From BCD now it has changed to binary, so binary value will be pushed. AH is just a side effect because AH has to be pushed on in that particular case, but now the AL value has been changed, right, by doing this particular operation. Okay, BP plus 12, that location gets the AX register. So now the value has been put back onto the stack, all right, and the next then statement will be restore the flags, so that the side effects of the subroutine is over. So first you do pop BX, the sequence is going to be exactly the reverse of push, right. So in push we had flag, AX, BX, CX and BP. In the pop case, we will be having entirely reverse sequence. So BP will be popped, CX will be popped, BX will be popped, AX will be popped. So like that, right? So from the top of the stack. That means first BP will be popped to the BP register, CL, this will be popped to the CX register, this value will be popped to the BX register, AX will be popped, flag register will be popped, right. So this is what till the pops are over, right, and then is the return statement. So return statement will load IP high and IP low into the program counter, and that is how the return is going to be effective. So return statement is there. That is the end of the binary BCD binary, because now we have returned and the code segment and so on so forth. So what you can see, this call statement BCD binary, right, that resulted into the pushing of this particular value, Thereafter the push statements, 5 of push statements. Then on the pop side, 5 of the pop statements will go on to do, right? 5 of these pop statements will do, and then return statement is going to control the movement of this particular thing. So now wherever our stack is at this particular location, right? So now after the procedure terminates, right, and you come to the return, that means PCA. So the next statement which is going to be executed after this is going to be pop AX, and pop AX will be referring to this AL and AH, and this AL value you have already modified, right? The parameter value has been modified. So the same value, like using the stack, you have utilized this particular stack, and AX now contains, the value of AX now contains the new binary value. Alright, so the new binary value is in AX. AH contains whatever value, it does not matter. AL contains that particular binary value. Now that binary value need to be stored in the memory, the space where we have created in the data segment for that. So it is going to be moved BL into AL. That is what this particular statement, and you just save it and then continue with the program. So this is how basically the subroutine calls work in assembly language programming. It is a wonderful thing because in assembly language programming, what you can do is lots of things. Basically, it's very powerful, right? So assembly language programming, this modular programming is a very interesting domain. In fact, most of your assignments, whenever we ask you to write one subroutine. So please make sure that you use proper pushes, proper pops, right? And then if you have to manipulate the parameter, you manipulate the parameter accordingly. Use stacks. It's very interesting. It is enjoyable also. And I mean, learning this particular concept is very enjoying. And you will be, once you implement this kind of a concept, you will feel really happy about this particular concept. And it is quite basic or internal of machine. And all the programs which you have written actually works like this. Right? Now you are knowing how exactly they work because of you make so many subroutine calls, but those programs work like this as far as internals are concerned. So study block 4, right? All the units you study, solve questions of CYPs in the block, solve question given in assignment and previous year question papers. Discuss it with us if you have any problem, and write to us on MCS 12 Facebook page. You can always write to us. Thank you, and thank you for being with me. Bye for now.